Okay, so differentiability. Differentiability means there is a derivative. Okay, that means the process for finding a derivative is called differentiation. So differentiability, all that means is you can find a derivative. It has a derivative. Okay, so we've been finding lots and lots and lots and lots of derivatives. There are some things that don't have derivatives, so they're not differentiable. Well, how do we know? How do we know? This is how you know. So the three conditions for differentiable must be continuous, has to be continuous, okay, at that point. Okay, so last two chapters ago, we talked about continuity. We're going to talk more about that today too. So we've talked about continuity. Um, Number two, no sharp turns. No sharp turns. Okay, the derivative going into that point has to be the same as the derivative coming out of that point, right? These little pluses and minuses mean from the left and from the right. So this means it's coming from the left, the negative side. So the derivative coming in has to be the same as the derivative going from the other side. Okay, and I'll explain what that means when we start doing problems. And then there has to be no vertical tangent. No vertical tangent at that. So it has to have a derivative, right? Vertical tangent means undefined slope. Okay. Okay, so there's two things to look for. When two curves meet at a sharp point, it is called a cusp point. The first one here, kind of two curves. You see how these two curves kind of meet? You see how these two curves kind of meet here at that point right in the middle at 0? That's called a cusp point, okay? And then a corner is when two lines or two segments meet right there, right? That's a corner. So neither of those is differentiable at that point because if I'm finding the derivative, so let's start with the cusp point. The cusp point, so as I'm finding the derivative, so at that point, at that point, at that point, at that point, right? It's negative. The derivative is negative at all of those points because the tangent line looks like that, right? But then as I start getting closer and closer to 0, it starts getting more negative, right? It starts getting more and more negative, right? Until I get to 0. What type of derivative, positive or negative, is at 0, 0? Positive or negative? Or neither? What type of derivative would be at this point right here? Positive, negative, or neither? Yeah, why neither? How does neither work? Yeah, the derivative is going to be look like this at that point. The derivative is going to look like a vertical, right? And vertical tangent means undefined for a derivative. So it's not going to have a derivative at that point there, right? So that's why we say it's not differentiable. That's why we say not differentiable at x equals 0 because the slope is undefined. The slope of the tangent line right there is undefined. And if it's undefined, the slope is undefined. It's not a number, right? So that's why a cusp point can't have, is not differentiable. It's differentiable everywhere else, right? It's differentiable everywhere else. All along here, it's differentiable. All along these dots here, you can find a derivative. Same thing over here, right? Just at that one point here, at 0, 0, it's not, okay, because of that. So that's a cusp point. How about a corner? How about a corner? So again, all along here, right, we can find derivatives, right? All along this line segment here, the derivative is going to be whatever the slope is of that line, right? Same thing over here. It'll have a positive slope over here, right? But what about at 0, 0? What about at 0, 0? What is the slope of the tangent line going to be there? So as I come in here, as I'm coming in here, my derivative is 0. Or sorry, my derivative is negative, right? As I come in here, my derivative is negative, right? So from the negative side, my derivative is negative because the tangent line, the slope of the tangent line is negative, right? It's going downhill. But then when I leave that red dot, what happens? The slope of the tangent line becomes positive, right? So that's where this guy comes in here. That's where this guy comes in, number 2. No sharp turns at C. No sharp turns. So you see how a corner is a sharp turn? It's a sharp, and then after that dot, it takes a turn to a different direction, right? There's no curve. If this was a curve like that, that's not a sharp turn. That's a slow, gradual turn, right? But a sharp turn means at a corner. The derivative from the left has to match the derivative from the right. Okay? Otherwise, if it doesn't, there's a corner. There has to have been a corner at that point. Okay? So that's why these two guys don't work. Okay? So number 3 looks like this, one of these guys here. Number 2 looks like one of these guys here. Number 1, continuous, continuous. Now, can anyone remember what the things are we need for something to be continuous? It's in your notes, but like I said, we haven't looked at it for at least a month or so. What are the things we need for something to be continuous? Yes, sir. Yep. We had 3 types, right? With discontinuity, we had discontinuity, right? We had jump discontinuity. We had vertical asymptote discontinuity or infinite discontinuity, and we had removable, which was holes, right? So how do we check? How do we check to see if something's continuous so that it didn't have those things? It was something with f of x. What did we find of f of x? The limits, yeah, we found the limits, right? This is what we did. We said the limit as x approaches whatever number we were looking for from the left has to equal the limit for whatever number we're looking at from the right, right? So from the left, it has to be approaching the same number as from the left. What I mean by same number is the same y value, has to be approaching the same y value, which if both of those first two guys, if both of these two guys are true, that means it has a limit. Overall has a limit. Good. And what does that have to be equal to? It also has to be equal to the what? The answer, yeah, the solution there has to be equal to an answer. It has to be a dot there, right? It can't be a hole there. That's how we check to see if there's a hole or not. That's how we check to see if there's a hole or not. If it's not equal here, that means there must have been a hole. All right? So you did that. You did that. First test, first quiz we had, or second quiz we had, dealt with that. Okay, it's in your notes. Might not remember it, but it's in there. That's how we check for continuity, because we're going to need to check for continuity today, because continuity and differentiability are very much aligned together. Okay, when they ask questions about differentiability, they ask questions about continuity. Okay, the reason we didn't do it back then, perfect world, we would do continuity and differentiability together, teach them in the same lesson. But the reason I didn't do it back then is because you had no idea what a derivative was. If I would have said, okay, a derivative, you're like, well, what's a derivative, right? So that's why we didn't do it back then with continuity. Okay. Okay, so here's a couple cheat sheet things. If you can show that something is differentiable, then it has to also be continuous. So if you can show that something is differentiable, you don't even have to check continuity. You don't even have to use this rule because it has to be. Okay? If something is continuous, if you check this and it's okay, you still have to check differentiability. It might be differentiable, it might not be differentiable. Can someone think of an example of something that's continuous but not differentiable? I'll give you two examples right there. Aren't these continuous? Can I draw this without picking up my pencil? Yep, just did it. Just did it, right? Continuous, but it's not differentiable at 0, right? So that's why if it's continuous, great, but we still have to check to see if it's differentiable. And then the last one, if it's not continuous, if you prove it's not continuous, if you show that these are not equal down here, then there's no way it can also be differentiable. Okay? So they're going to ask. They're going to ask this question. You can look at it on the next slide. They're going to ask this question. Is it continuous and differentiable? Is it continuous and differentiable? So which one should we check first? For continuity or differentiability? Which one should we check first? Continuity? If it's continuous, right? If we say yes, it's continuous, do we also have to check differentiability? Yep, we do. Because it could look like this, right? But if I check differentiability and we say, yeah, it's differentiable, then I don't even have to check continuity. Continuity has to be. Or you can check both. You can always check both, but looking at your tests, a lot of you like to take shortcuts, right? Which is fine. Sometimes shortcuts work, but just make sure it's an okay shortcut. A lot of you were taking shortcuts on the test, like on the FRQs, and the shortcut wasn't okay mathematically. There was some things that were wrong with it. So just make sure if you take shortcuts that it's mathematically you have an argument there. Okay? So same thing. If we check differentiability, okay, how do we check differentiability? Right there. Here are the rules. Here are the 3 rules here. Well, continuity is one of them, right? Isn't continuity number 1? So we have to check that. So the first thing we have to do is check continuity. And then we have to check, okay, it's continuous, check. Is the derivative coming in the same as the derivative going out? Positive, negative. And then we have to also check if there's no vertical tangent. Well, 2 and 3 are kind of the same. 2 and 3 fit into one rule. If we can check one, we can check the other. So these 2 are really one. If I check this here, so 2 things I got to check with differentiable. I got to check this, and I got to check this. Those are the 2 things you got to check to see if it's differentiable. Okay? All right. Okay. Let's look at the first one. Let's look at number 1. Okay. We have to check, is it differentiable? Is it continuous? Is it both? Or neither? At the value where the rule changes, where the function changes. Okay, so where does it change? Where does the function change? It says changes here. Where does it change? Where does f of x change? 14, right? At 14, before 14, every number before 14 and at 14, we're going to use this guy here. Any number after 14, we're going to use this guy here. So that's where it changes. So we're going to check at x equals 14. Okay. Okay. So the first thing we're going to do is check continuity. Okay. So that laundry list of things that are equal, I have to check to see if they're equal. I got to check to see, are all of those equal? Okay. So the limit as x approaches 14 from the left for f of x has to be equal to the limit as x approaches 14 from the right, which is equal to the overall limit. And then I have to check f of 14. Okay, those are the things I have to check. So I have to get answers for each of these. Okay. So how do I get the first one? How do I get the answer to this guy here? You've done this before many, many times on tests and quizzes, on assignments. How do I do it for this guy here? So we're not derivative yet. You're right. That's what we're going to do for differentiability. We're going to do that. What do I do here, though, for continuity? Not derivative. How am I going to do this? We'll get to differentiability later, but for right now, I'm just checking continuity, what we did back in chapter 1. Just plug it in, yeah. Just plug it in from the, well, it's coming from the left side, right? It's coming from the left side. So which one am I going to use if it's coming from the left side? The top one, right? So I'm going to plug in 14 to the top one and see what I get. All right? So I get 14 squared plus 7 times 14 minus 20. 14 squared is 196. 7 times 14 is 2, carry the 98, minus 20. Let's see, add them all together, we get 294, 314. Yep, unless someone has a better answer. I'll take it. All right. We have to check to see if that's equal to the next limit, the limit as so I'm going to plug in 14 for which one? To the bottom one, yep, to the bottom one. So plug in 14 there. So 14, oops, 20 times 14 minus 6. Let's see, 280. Is that right? 140, double 140. 280 minus 6 equals 274. Is this supposed to be 274? Okay. All right. If those are equal, that means this guy has to be equal too. I can check it again, but didn't I already check it? Which one would I plug in for? Which one would I plug in 14 for this guy? The first one, right? And I already did that. And if the first two are equal, that means by rule, the second two have to be equal. And then this one says the answer at 14. Where would I plug in 14 for this guy here? The first one again. Yeah, the first one again, because that's where it fits on here. 14 is equal to 14. So I already did that again. I already did that on the first one. So we say f of x is continuous at x equals 14. Okay, that's how you check continuity right there. A lot of you had some interesting takes on how to find continuity. I think it made sense in your head, but to someone reading it, you have when you write down problems, a lot of you when you on your FRQs, you kind of just like it looks like your just brain just kind of vomited stuff and it's all over the place. And I know it makes sense to you, but you got to think of someone who's reading it, not just me, but someone who's reading it. Is it clear and concise? Okay. So this is clear and concise. It shows you exactly what I was doing. I was checking this right here, right? What's my answer? I used arrows to show my answer. I used equal signs here, and then I explained what it all meant. That's what I need you to do when you're checking things like continuity, okay? Because a lot of you, I know it makes sense to you because you just write down stuff and you're just writing down everything you know, which is fine, but you got to think someone's going to grade this, okay? It's got to make sense. So make sure that it makes sense with what you're trying to do, okay? Okay, so continuity check. We got continuity. So continuity, so it is continuous. Now let's check differentiability. Okay. Differentiability, the first rule, top left-hand corner, what does the first rule say we have to do? Top left-hand corner of your paper, what is the first thing? Continuity, right? We already did that check. Okay. Number two, go back to what Sebastian said. What were you saying earlier about derivatives? We have to check derivatives. We have to find the derivative coming in and going out. So it's kind of like a limit, right? Approaching, right? So this is what we're going to do. We're going to find the limit as x approaches 14 from the left, not for f of x, for f prime of x, for f prime of x. We're trying to see what the limit is as it gets closer and closer to 14. Okay? And then we got to check that with the limit from the other side. The limit as x approaches 14 from the right, not for f of x again, for the derivative. For the derivative. This looks very familiar, right? We just did that stuff. The only difference is it says f prime. So how do we find limits? What did we do earlier, just right above, to find limits? Right above that problem, right above on mine, right about here. What did we do to find those limits? We plugged 14 into f of x. Are we going to do that for this guy? No, not f of x. We're going to plug it into f prime of x. Yeah, f prime of x. So let's go up here first. First thing we're going to do is we're going to go up here. And on the side here, we're going to figure out what f prime is. We're going to find the derivative of f. Okay, so here before 14, or at 14 and before, I'm going to find the derivative there. It's just a regular explicit equation, so it's 2x plus 7, right, when x is less than or equal to 14. And then the bottom one is just going to be 20 when x is greater than 14, right? That's the derivative. So now we're going to use that guy to do the questions below. Okay. So we're going to plug in this guy to the derivative. Which one, the top one or the bottom one? The top derivative or the bottom derivative? The top, yeah, because it's from the left, right? The left-hand side. So 2x plus 7. So 2x plus 7. Okay. So 2 times 14 is 28, plus 7 is 35. Okay. We're trying to see if that equals this guy here. So plug in 14 to the other equation. What do we get when we plug in 14 to the other guy? It's 20, right? It's not, it can't plug it in anywhere. It's 20. So they're not equal. They're not equal. So we say f of x is not differentiable at x equals 14. So it's continuous, but not differentiable. Which one? How to get 20? Oh, okay. So it's about f of x. We would use f of x here. F of x is not differentiable at, yeah. So we're saying f of x doesn't have a derivative because f prime didn't work. Yeah, it's always referring back to the original because that's what we were doing. So it's not differentiable. Is that okay? Does that fit on our list? Let's go back up here to our cheat sheet here. Does that defy any of these bullet points here? Because if it does, we did something wrong. But if it's okay, then we're good. Did it defy any of these bullet points here? If it's differentiable, then it must be continuous. If it's continuous, then not necessarily differentiable. If it's not continuous, then it cannot be differentiable. So did it defy any of those guys? No. It fell, actually, it said exactly what this is right here. If it's continuous, it might be differentiable. You got to check it. That's what it's saying. So we're good. Okay. So it's continuous, but not differentiable. So what does it look like? What's causing that? How is it continuous, but not differentiable? Yep. It looks like one of those guys, right? It probably at 14, it looks like one of these guys here. One of these guys here at 14. Continuous, but not differentiable. Okay, so it's either got a corner or it's got a cusp point. Okay. How can I tell which one? Because you can tell which one. How can I tell which one? A cusp point or a corner? Mhm. Yeah, exactly. Exactly. You can tell because for it to be a curve, it can't be linear, right? For it to be a line, it has to be linear. Well, let's go look at our here. The original, the bottom part is linear, right? But the top part is a parabola, it's a curve, right? It's a curve. So that means it's got some curve to it. So it's going to be a cusp point. Okay. Yeah, the only way for it to have a corner is if it's to have two linear equations going. Okay. They usually don't ask that. I've never seen a question say, is it a cusp point or is it a corner? So, but it's just, since we were there, I was just kind of, might as well ask. Okay. All right, so the next one, do number 2. Do example number 2 on your own. Example number 2. Give you about 5 minutes to do that, and we'll talk about it. Okay, so I checked it. I checked continuity. So they wanted me to check where it changes. The only place it could change is at -2. The function changes at -2. It goes from the top function to the bottom function. So I checked -2, plugged in -2 to the top because that's the less than. I got +6. And then I plugged in -2 to the right. I got +6 as well. That means there's a limit at +6. And that means, and then for this guy, plug it into this guy again, since it's equal to -2 there. I didn't do it because I already had done it. 6, so that means it's continuous. So continuity, it's continuous. But again, it might not be differentiable, so we got to check that. So I haven't checked it yet. But I did write down how I was going to check it. This is your explanation on how you know, right here. Okay? So like I said, when we do this, sometimes you'll see students write paragraphs. I don't need paragraphs, okay? Because most of the time the paragraph won't be correct. This is all the writing I need here. This explains exactly what you're doing. You're checking to see if that is equal to that, okay? That's what you're doing, okay? So in order to do that, though, I got to check the derivative. I got to find the derivative. So 2x plus 11 and 7. Okay. Oops, why did I put 14? It's supposed to be -2. 14 was the last problem. Okay. So I'm going to plug in -2 to the top derivative. So when I plug in -2 to the top derivative, it's 2x plus 11. So 2x plus 11. So I get -4 plus 11, which is +7. I'm going to do the same thing, but plug it into the other guy. Well, the other guy, there's nothing to plug in. The other derivative, it's only 7. So f of x is also differentiable at x equals -2. Okay. All right. So we're going to skip these because these problems are going to take a little longer. So we'll do those on Monday. So let's skip those. Let's go to number 5. Okay, it says, given the piecewise function, answer the questions at the bottom of the page. There are no questions at the bottom of the page. The question at the bottom of the page, cross that part out, is, are they continuous and are they differentiable? Okay, so check those. So do number 5. This will be the last thing we do today. Do number 5. Same thing, same question. Is it differentiable and is it continuous at x equals 0? Okay, so just so we don't run out of time, get started. So continuity, that's the way you set it up. So 0 from the left, 0 from the left. So if I check 0 from the left, I'm going to plug it into the top one. Okay, so anywhere there's an x. So 3 times the natural log of 1 minus 2 times 0 plus 1. Okay, so 3 times the natural log of 1 plus 1. What's the natural log of 1? 0. Yep, the natural log of 1 is 0. So it'd be 0 plus 1, which is 1. That natural log you can do. Some of them, like the one on the test, it was like natural log of 2.5 or 2.5. Leave as natural log of 2.5. Don't do that one. Leave that. But the natural log of 0 is the natural log of 1 is all something you should memorize, or at least know how to do it. How do I know that the natural log of 1 equals 0? How do I know that's true? Exactly. This means that E, just like Sebastian said, to what power equals that number there? Anything to the 0 power makes 1. Okay, so it's going to be 0. So the natural log of 1 is always 0. Okay, this guy here, plug in 0 there, I get negative 6 times 0 plus 1. That's just 1. Okay, so that means this guy is going to be equal to 1, which means this guy is going to be equal to 1. Continuous at x equals 0. Okay. Last thing, differentiable. I got to find the derivatives first. So let me go find the derivative of these two guys. Okay, so the derivative of the bottom is easy. It's just negative 6. The derivative of the top, the derivative of this guy here. Let me do that up here because it's going to leave a little bit more room. So we have (2x plus 1). Okay. If I see anyone pack up, the next test is going to have lots and lots of these. That's a promise. Because if you're packing up, you're like, Mrs. Flores, this is way too easy. Okay. Okay. So here we go. 3 times, and then the derivative of this guy here, which you had on your test. You had a natural log derivative. That was FRQ number 1. First thing you do is you put 1 over whatever it is times the derivative of that guy there. Right? So that's going to be negative 6 over 1 minus 2x. That's the derivative. And then plus 1, you got the derivative of plus 1 over here, but the derivative of plus 1 is just 0. Okay, so that I'm going to move down here. Oops, no, I'm going to write over here. Sorry. Negative 6, 1 minus 2x. Okay. So now I got to plug in 0 from the left. 0 from the left, negative 6 over 1 minus 2x, which is negative 6 over 1. And then the other one is negative 6. It's just negative 6, right? So it's also differentiable at x equals 0. Okay. Alrighty. So we'll finish the rest on Monday. The only assignments are, you have 2 assignments. You have finish the scavenger hunt if you haven't already, and upload it. The second one is there's a Delta Math assignment that I believe is due today or Monday. Tonight, it's due by today. Okay, so if you haven't done that, okay, those are the only 2 things. I'm not adding anything to that. Okay, so just make sure you get those done. Upload the work. Okay. All right. Thank you for waiting. Now you can pack up.